Welcome to the first lesson of data structures and algorithms. This lesson is called Abstract Data Types. Before we begin, this is the color coding that we use for the whole lecture, actually for the whole series of lectures. So in red, we have highlighted the most important points, and then blue, green, and purple with the order of decreasing importance, with purple being actually off topic but necessary. So these are the learning outcomes of this lesson, right? So upon the completion of this lesson, you'll be able to understand abstract data types. You'd be able to describe what abstraction is, and then you'll be able to define abstract data types and describe their uses. Abstraction. This is probably a word you have heard in normal life, right? We don't have to talk about programming. So when you hear the word abstract, usually it means something not quite real. So you can think of abstract art, for example. It doesn't really show pictures of people or buildings. It's some artistic concept which is not quite real. So the abstraction is a separation of relevant from the irrelevant when it comes to the more scientific and, let's say, mathematical domains. This is a bit different from the art domain. Let's look at a concrete example in arithmetic. So if we look at this small figure at the bottom of the slide. So it has a small picture of some aeroplanes. On the left side, we have one aeroplane plus two aeroplanes. So we have equal sign. It says equals to 3 airplanes. So this is nothing new to you. But what is the abstraction that you learned? You know 1 plus 2 airplanes is 3 airplanes. And the airplanes are real objects. The abstraction or the abstract concept behind that operation is that 1 plus 2 equals 3. So that's the abstraction that we use in arithmetic. So once you know this abstract rule, you could apply it to any instance or object. It could be fish or birds, like here, 1 bird plus 2 birds equals 3 birds. Let's look at a bit more advanced example beyond arithmetic. So there are no perfect circles. There's always some imperfection if you zoom down to the highest resolution. However, the theoretical or the imaginary perfect circle with radius r has a circumference of 2 pi r. That's also an abstract concept. You cannot actually build a perfect circle to show this is perfectly true. However, with a good enough approximation, this value of the circumference applies to things like bicycle tires or planetary objects, which are circular or spherical, or even a small circle that you draw using a compass. Okay, now let's try to look at how this concept of abstraction can be applied in programming, in computer programming. The concept of abstraction in the domain of programming applies in a couple of ways. Let's first look at data abstraction. So data abstraction hides the details of the data so that it's easy for the programmer to work with. So the idea is, when there's a certain type of data that you're using in a computer program, the underlying mechanisms of how the data is stored and how certain things are implemented, so how the data is stored in the memory, for example, this is completely hidden away for the programmer at the time of writing the program. This makes life easier for the programmer because you don't have to think of low-level, machine-level memory operations or memory details. So that's data abstractions. It hides away the details of the data representation. Let's, in certain engineering terms, so we first look at things like arithmetic and circles. So in engineering terms, we can think of it as a person using a mobile phone. So do you know, or you might actually know, but you don't have to care about how the internal electronics and the program works inside the phone when you browse the internet using your smartphone. You just pick up your phone, open the browser, and search for whatever you want. You don't have to think about the network layers or the application layers, anything. So these layers are abstracted away. So it's shown in a bit more detail here. Basically, what you see as the mobile phone is a black box. You only see the superficial usage. So you would like to use certain apps or use the internet to browse some things or watch videos on YouTube. You don't need to worry about how these features are implemented. So it's a black box. It's abstracted away. What you understand or what you need to interact with is just the interface. That's where you give the commands, open the browser, type the search keywords, things like that, right? So the interface is what you deal with, not the details of implementation. So the process of isolating the implementation details and extracting only the essential property from an entity is referred to as abstraction. Right? So data abstraction asks that you think in terms of what you can do to a collection of data. You don't have to worry about how to do these operations as yet. At the type of writing a program, you only work with the interface of these data types. So that's data abstraction. Typically speaking, data abstraction is only one aspect of abstraction in computer programs. There's a second one called function abstractions. In this lecture, we only talk about data abstraction. So when it comes to abstraction, when it comes to data abstraction, we focus on what operations are needed by the data and the functions. And the abstraction focuses on the purpose of the function. What should the function do? In the definition of abstract data type, ADT, in short, ADT is a data type whose properties, domain, and operations are specified independently of any particular implementation. So ADT only mentions what operations are to be performed, but not how these operations will be implemented. Right? So it does not specify how data will be organized in memory. It does not specify what algorithms will be used for implementing the operations. It only specifies what operations can be performed, right, without the implementation details. So let's look at an example. So integers are physically represented in different ways on different systems. So in one system, an integer may be represented by a binary coded decimal. On another system, it may be a sign and magnitude binary. On another system, it may be represented by 2's complement binary notation. So you might or might not be familiar with these terms I just said, right? These different implementations of the integer on different systems. But did it ever stop you from using integers in your computer programs? I doubt it. So it didn't really matter to you how these are represented. So in this slide, we have actually visualized the decimal representation of how a certain binary value is actually implemented or represented on different systems. So this binary value, if it is an unsigned binary value, this is the value, 153. If it is sign and magnitude binary, then the decimal value of it becomes -25. Once complement, this value is actually -102. In 2's complement, its decimal equivalent is -103. If it is a binary coded decimal, the same binary, its value becomes 99. So these are 5 different possibilities of decimal equivalents of this 8-bit binary number we see on top. So the way that the integers are physically represented in the memory determines how the computer manipulates them. So sometimes you have compilers for compiled languages. For interpreter languages, you have interpreters. However, as a Java programmer, you do not usually get involved at this level. You just simply define integers and then work with them in your computer programs. So when you write a program, let's say in Java, and when you use integers as a data type, what you need to know is the set of operations that are allowed on integers, right? So we have assignment operations, addition, subtraction, multiplication, division, and modulo arithmetic. So let's consider the statement where we write a small equation from physics lessons you might remember. Distance equals rate multiplied by time. Rate could be even velocity, right? Distance equals velocity into time. So here, distance, rate, and time are variables that represent real numbers. So real numbers could be a floating point number or maybe integers, right? Mostly they are floating point numbers. So the concept of multiplication does not depend on whether the operands are integers or real numbers, right? Multiplication is still multiplication. However, when you look at the internal details of implementation, the multiplications of integers and multiplications of floating point numbers might be implemented differently. However, because of the concept of abstraction, you do not need to worry about it. You just implement the multiplication of the two numbers you want in your program. So this hiding away of details, let's say in Java, you have this int, the integer data type. It hides away the implementation details. And we call it encapsulation. So Java has encapsulated the integers. Without knowing how multiplication or division is implemented, you can use multiplication and division in your programs. So this word encapsulation comes or kind of refers to also what you do when you get some medicine from a doctor, right? So you have this capsule, certain medications are encapsulated by these manufacturers of this medicine. It's encapsulated into a capsule. You are prescribed this medicine by a doctor. So for your illness to get better, you just swallow it without having to worry about the biochemistry of that particular medicine. It's a very similar thing, or somewhat a similar concept to abstract data types, where things are encapsulated, where the details are encapsulated, and you only work with the interface. So if the data structures of the data types are encapsulated, as we told earlier, how can the programmer get to them? How can the programmer use them? So this is why we want operations, the set of operations that are defined on that particular data type. So operations are provided to the programmers. When it comes to int or any other data type, the operations are provided to the programmer so that the programmer can create, access, and change the data in their computer programs. So for this encapsulated data type int, there are a certain set of Java operations provided. So you can create an int variable. All right, you can declare them in your programs, and then you could assign values to these integer variables, and you could use certain arithmetic operations on them. Right, you could change the values of these variables by performing arithmetic operations like plus, minus, multiplication, division, and modulo. So in this slide, we have a visualization of how the data type int in Java has been encapsulated. So it's packaged or encapsulated into a neat black box where we have the description of the data. So we have type int, we have the value range from minus a value at the plus maximum value. And inside you also have listed the operations that can be performed on this data type. So although it's shown, it was shown as a black box. It means the implementations are hidden away from the user or the programmer. Right? They're just hidden away. They still exist. So there are two goals that we have achieved with this type of design, right? So with this approach to having abstract data types. Number one is we can reduce the complexity. So don't have to always worry about how things are implemented. There are operations defined. So there's an interface. You only have to know what the operations defined in the interface are doing and how to use them. So that way we reduce the complexity. The other one is to protect the data that has been abstracted through the encapsulation. So with encapsulation, since you hide away the implementation details and you only expose certain well-defined functions, you automatically can enforce the programmer what they can do with the data type. That's what we mean by the protection that we achieve using data abstraction. Let's look at the definition of abstract data types, or the formal definition. The set of all possible values, that is the domain, of an encapsulated data object and the specifications of the operations that are provided to create and manipulate the data is defined as an abstract data type, ADT. So when the abstract data type is implemented, right, when you do an implementation of it in Java, that will lead to a concrete data type. So all the Java built-in primitives, the built-in types or the primitive types are abstract data types. So you can declare variables of those types without understanding the underlying implementation. So to summarize again, the programmer can then initialize, modify, and access the information held by those variables, right, using the operations provided or defined with the data type. So essentially, you don't have to worry about the implementation of the methods. You just use the methods. So now we are going to look at some examples for abstract data types. So we are going to look at bag and set. So we can define the ADTs, the abstract data types, as follows. But let's first look at bag, abstract data type. So a bag can be defined as a collection of objects. So bags are containers that can hold objects or things. So the fundamental operations of all bags are given here in this list. So you have the add operation. You can add an item. You can put something in the bag with the add item. Then you have the remove item. Item is again the argument. It's an object. So you can remove an item from the bag, right? Take an item out. You could clear the whole bag by calling this method, the clear method. Then you could count how many things are in the bag currently using get frequency of item. So given an item, how many of it are there in the bag currently? To see if the bag is empty, you could call this method on the bag, is empty. To check to see if something is in it, right? If check if a certain item is in it, you say contains and pass the item as the argument. If you want to know how many items are there in total in the bag, you could call this method get current size. If you want to look at all the contents of the bag, you could call the display method. So in this slide, we visualize some more details of all the methods that we discussed in the previous slide. So basically, for each method, we check if there's a return value and what that value is. So some of the methods have a return value. And for all the methods, there's also a post condition. So what are the changes that has happened to the ADT bag after calling that method? So let's look at them one by one. So the add object method, once you add an object, the post condition is the given object, which is passed as an argument, is in the bag. You have this Boolean. Boolean is the type that's being returned. Right. So contains object. When you call that operation, it returns true if and only if the given object is in the bag. The post condition is that the bag is actually not changed. It's the same bag, right? Because we are just doing a check. Then we have the get first method, which returns an element of the bag. The first element of the bag. There also, the bag is not changed. Then we have another method, get next, which returns some element of the bag other than those already returned by the last call, right? So if you first call get first, it will return the first object. And then if you call get next, it will call the second object. And if you call get next again, it will return the third object, like that. But at the very end, the call will return null. If all the elements have been accessed, right, it will return null at the very end. Here also the post condition is that the bag is not changed. The return type is an object. Then we have the remove object method. It returns a Boolean type. And it returns true if it returns true if you can successfully remove an object, and then it returns false if that object is not the bag in the bag, right? Then you cannot remove that object which is not in the bag. The post condition is that then that object is removed from the bag. However, in this particular function, we are not concerned about the post condition. In this function, we are concerned about a precondition. So for this to work, the object should be in the bag. So that's a precondition. Then you have the integer valued return. The return value is an integer. You could call the size method on the bag. It returns the number of elements in the bag. Here also the post condition is that the bag is not changed. So the next ADT, example ADT we are looking at is sets. So a set is different from a bag because a set is a collection of unique objects. You cannot have the same object twice. You cannot have two apples or two oranges. You can only have one apple, one orange, right? There are no duplicates. So the preconditions and the post conditions are a little bit different. So mainly the preconditions are different. So let's look at the add method. So it returns a Boolean value if it is successfully added, if the object is successfully added. it's returning true, otherwise false. However, there's a precondition. The object you are going to add should not be in this set. First condition is the given object is in the set because you have added it. Then we have this contains method. It's the same as before. Returns true if the object is in the set. So as before, if you now go to the remove object, it's again the same. So try to look at the differences of these function signatures and their definitions, right? So there are different properties that we expect from bags and sets. So accordingly, the details, what the method is doing can change. The preconditions or the post conditions or both can be different between these two abstract data types. The main difference between these two types, so both of them are containers. The difference is that a bag may contain duplicates, but a set will not allow duplicates. Otherwise, they are both unstructured and unordered collections or containers. These two data types, abstract data types, have two transformer methods. They can also be called as mutate operations. They change what's contained in these data types. Right? So these mutate operations or transformer methods are add and remove. You could add objects or you remove objects. And these are transformer methods or mutator methods. Then you have observer methods. Right? These are accessor operations. They don't modify the contents. They are there to observe what's in there. So these are contains, get first, get next, and size. So how to spot observer methods and mutator methods? You could look at their post conditions. So for observer methods, it should be very clear that the contents don't change. They are there only to observe. However, for mutator methods, the contents can change, and this is reflected in the post conditions. So let's look at the observer methods and the mutator methods in a bit more detail with reference to these two data types, the abstract data types, bags and sets that we discussed. So if you look carefully, you should be able to see that the four observer methods are the same for bags and sets. Only the two transformer methods or the mutator methods, add and remove, are different between bags and sets. So let's first look at the add methods. So if we assume that the overflowing problem is sorted out, if it is taken care of, right? If we think that there's no limit to how many objects you can add, the bag data type, the bag abstract data type, using the add method defined for the bag, you could insert or keep on inserting any object, even if you have added that object before. But this is not the case for a set, because by definition, a set does not allow duplicate objects to be contained in the set. That means for the set abstract data type, when you define the add method, you have a condition that has to be satisfied. That condition is that the object you are going to add is not already contained in the set. If that object, let's say case 1, the object is not in the set, then you call the add method. For a new object, you add that object. So the precondition is satisfied, the object is not in the set. After adding that object, the add method returns a value true in this case because it was successful. However, for a bag, you don't need this return value because it does not need to have any precondition, because as long as you give any object, the bag can keep on adding that object. So it's always a success. So you don't need to define a return value, right, for the bag. So that's never going to fail. The add method for a bag is never going to fail. However, for a set, the add method can fail when the object you are trying to add is already in the set. So next, can you explain the difference between the mutator method, remove, with reference to bag, and set? You can take a couple of minutes to think about it. You can probably pause the video while thinking about it, and when you're ready with the answer, you can continue. So let's see what happens when you try to remove an object. Is there a precondition for bags and sets? Yes, because you cannot remove an object from a bag or a set if the object is not already there. So that's the precondition. However, in post conditions, there is a difference. So in a bag, as you know, there can be duplicates. So just because you remove one apple, if you just remove one object, you cannot guarantee that there are no more apples. There are no more the type of object that you remove from the bag, because there can be duplicates. However, it's not the case. It's not the case with the sets, because in a set, there's always just one copy of one object type. So if you remove object type apple from a set, you can guarantee as a post condition that there are no more apples in that particular set. So that's the difference between the two post conditions in the mutator method, remove, with reference to sets and bags. In case you haven't figured it out, I'm sure you did, a precondition is a condition that's assumed to be true before the operation begins. So before you add an element in a set, the precondition is that that object is not there. Right? It has to be true. A post condition is a condition that is guaranteed to be true after the operation ends. So if you remove an object from a set, you could guarantee that object is not there anymore in the set. Right. So the advantage of ADTs is that they can be used in algorithms. Right? They have, each ADT has their own properties, right, on unique behaviors, as we discussed with bags and sets. So you should use the appropriate ADT to certain algorithms when you implement it. So let's look at how to write an algorithm that removes all instances of a given object from a bag. You could pause the video for a few minutes and try to write some pseudocode or even actual code. You could actually write a Python program, for example, or a Java program, and then we can proceed. Okay, I hope you have written down some pseudocode at least to do this task of removing a given object, removing all the instances of a given object contained in a bag. So yeah, this is the pseudocode that we are going to discuss now. Basically, so algorithm 2.1, the task is remove all instances of an object or element from a bag. So what are the inputs to the algorithm? We have a bag B and the object to be removed, X. The output will be the number of objects removed. So right now, how many times have you seen this object? And all of these instances should be removed. What's the post condition? After calling this method, the bag B contains no X objects, right? There has to be zero number of instances of X inside the bag. So what's the pseudocode now? Step 1, let n be the integer 0. So n equals 0. Next step, if B contains X, then it's false and return n. So this means if B dot contains X, if this returns false, it means X is not inside the bag. Then you return the value of n. So just think, if we just started the algorithm, so step 1, n is 0, and in bag B, you don't have any copies of X, then this part becomes false. Then the algorithm stops and returns n, which is 0. However, if this is true, if B contains X, you go to the next step. Then you call the remove method. You remove B from X, and then you add 1 to n. So n becomes 1. So now n is 1, and then we go to step 2. So it's a loop. Again, we check if there are any copies of X. If there are no more copies of X, this part becomes false. Then n is returned, and the algorithm is stopping its iteration, right? It returns. Then what was the value of n? It was 1 because we added 1 in the last iteration. If there are more copies of X, you can see this part becomes true, and then we go to the third step again. Then we can remove that copy of X and then add 1 more to n. Then the n becomes 2. Again, you could go back to the loop. So you iterate this whole loop, incrementing n every time you remove one more copy of X, right? So at the end, when it's returned, the return value n contains how many times, how many copies of X you have removed. This slide contains, apart from what I described in the previous slide, this slide contains a concrete example, right? With the bag containing 6 oranges and 10 apples, 3 avocados and 2 lemons. And if X is avocado, then how many iterations does it need? Right? You could calculate this for all of these individual fruits. How many iterations? Basically, the number of iterations equal to the number of that particular type of fruit is in the bag. So you could do this exercise yourself. and C. So when we look at the source code of that previous task, you probably noticed that we used the two methods, contains and remove, without having to worry about how they're implemented. Now that's the power of abstract data types. You should only know what you can do with the data type. You should know what operations to call, and that's it. You could write the program by using those methods. So the discussion of abstract data types continues from the abstract part into concrete data types, because without having a way to realize objects, right? Without being able to create real objects and to be manipulated, the use of abstract data types would be not very interesting, right? So for it to be interesting, we have to go from abstract data types and implement concrete data types. So the realization of concrete data types in Java has this sequence of developments. So first you have ADTs, the abstract data types. Then from those you could define the interfaces, right? You have the interfaces for the abstract data types. Once ADTs are transferred into an interface, you could then implement a class using those interfaces. So classes are implemented using interfaces. And then once you have the classes, you could instantiate objects. So that's the sequence of developments that takes place when you start with abstract data types until a realization or instantiation of objects. So let's go into the code. We want to have a look at the realization process, starting from an abstract data type to instantiating an object. So first, you have to have the interface defined for the bag. So this is an example of how we do it in Java. You have public interface bag, you have some method definitions. Sorry, these are the method prototypes. We don't have the implementation details. It just tells you some basic facts, like the method name, what kind of argument it expects, and what kind of return value it has. But these are just method prototypes. And this part here, the whole code snippet, corresponds to the interface of bag. So as we discussed before, let's say for the first method that we see, add the inputs, the argument is an object, right? There's no return type, return value, but contains takes an argument object and has a Boolean return value. Right? It returns true or false. Get first and get next, they have return types of object, so on and so forth. So in order to create a bag object, to instantiate a bag object, the interface itself is not enough. We must first define a bag class that implements the bag interface. So that's something we are going to look at in the next couple of slides. and we'll be using a simple data structure called an array. You will be learning much more about arrays in the next lesson. However, we'll be using it to implement the bag interface. This is the source code for the class ArrayBag. It implements the interface that we discussed earlier, named bag. So the first line says basically that. You might remember from your object-oriented programming in Java classes. So first line says public class ArrayBag implements bag. So next line, we have a private object, square brackets, objects equals new object within square brackets 1000. So what that line does is that we initialize an array of 1000, size 1000, and we name it objects. You'll be learning more about arrays in the next lecture. For now, just understand or just know that this line basically creates an array of size 1000. So later on, you could be adding 1000 objects into it, up to 1000 objects. Next line, we have private int size, comma, I. So this line defines two variables, two integer variables, size and I. Size basically is used to keep track of the size of the bag, of the array bag. And the variable I is basically an index variable that can be used to iterate within this bag of objects. So next, you'll see there are a few methods defined. For example, public void add. This is the add object method. So the argument is an object. Basically, it's taking the object as an argument and then placing it inside the objects array at the current element plus 1 position of the array. And then it increments the size variable. The next method, you can see it's defined public boolean contains object. So it returns a boolean value if the array bag contains the input object. So basically, it has a for loop. It iterates over the array objects. And if a match is found in the array, it returns true. If there's no match found, it returns false. So that's how the contains method work. Then you have public object get first method. So it does not require an argument because it basically gives out returns the first object in the array. So in the next slide, we have the continuation of this class definition. So we have a public object get next. So get next meaning whatever the I value you have, which stores the currently accessed index of the array. It increments I, so you can return the next object. Right? And if you have reached the limit of the array, it returns null. If there are no more objects, it returns null. That's how the get next method works. Then we have the remove method, public boolean remove. So it takes an object as an argument, as the argument. It basically, with this for loop, it iterates inside this array bag, inside the array of the array bag. And whenever it finds the first match to the input object, it removes the object from the array and reduces the size of the array by 1. And for this, we use a system.arraycopy, which is a special method to copy a set of objects from one array to another array. Could be from the same array, right? Also, in this case, it copies to and from the same array. And we'll be discussing this method in a bit more detail later, because that's the core part of this remove method. So once an object is successfully removed, it returns true. So for it to be successfully removed, the condition is it has to find it in the array. So if it is not found, it will return false. And nothing is obviously removed. And then you have another method to return the size of the array. So this slide highlights some of the things I already mentioned when I showed you the source code in the previous 2 slides. So the important idea is that when you implement an interface, when you define a class that implements a certain interface, in this case, we define the class array bag that implements bag, right? Bag is the interface. So all the operations or methods described in the bag interface are implemented in the class array bag. And when you want to create an array bag object, you can do it like this. So bag of fruits equals new array bag. So with that kind of instantiation of an array bag object that we named bag of fruits, you should remember from the code, it allocates a size 1000 array. So the bag can hold 1000 objects, right? So after defining that, you could add elements or objects to your bag of fruits. That's the instantiation of the array bag class that you named as bag of fruits, right? So for example, once you define the bag of fruits array bag, you could keep adding different kinds of fruits like this. So different kinds of objects. So in this case, we define objects as fruits because it goes with the theme of the example that we are considering here. So bag of fruits dot add, you add an apple. Bag of fruits dot add lemon. Bag of fruits dot add avocado. So if you just visualize the contents of the array bag, which is called bag of fruits, you see the fruits that we added. So we add an apple, we add a lemon, then we add an avocado. Note that the objects we add are just string objects. So once you have added some objects, you can check whether an object is inside your bag. You should remember the method contains will check whether a particular object is contained within the bag. So if you call this method bag of fruits dot contains lemon, so since we already added the lemon, it should return true. If you type this, if you execute this bag of fruits dot contains orange, it will return false because we did not add orange into our bag of fruits. The get first method will output the first object in the array, and the getNext method will fetch the subsequent items of the array. The Arraycopy method has a few important arguments. Object src, int src pos. Object dest, int dest pos. Int length. So the two object arguments src and dest specify the array to copy from and the array to copy to. So as the name suggests, it's a method to copy an array from one array to another array. The src pos integer argument refers to the starting position in the source array. Dest pos int argument refers to the starting position in the destination array. So it's copied, the copying is done from this source array from position specified this to the destination array determined or specified by the position dest pos. Length specifies the number of array elements to copy. So from src pos, position src pos, a number of elements equals to length is copied from the source array to the destination array, and at the destination array, the starting position to which the array elements are copied to is specified by dest pos. So these are the arguments, right? So the input is in our code, that removes all the instances of a given object from the bag. So this is the code snippet of the remove method. It basically copies from the source. So here, this is the source objects, the one that holds all the elements in the array. All the elements of the array bag named bag of fruits, for example. So from position I plus 1. So when you pass an object, and if the object is found at position I, you copy from position I plus 1 to the same array, but to position I, which in effect deletes the object at I. Right? So the size is size I minus size minus I minus 1, because you copy all the elements after the object I without the object I back to position I. So it will be easier maybe if you write down a small example, maybe with 5-6 elements of an array, and try to see how it works as a little exercise. So after doing that, you should also know that the size of the array has decreased by 1. That's done by this line with the minus minus, the decrement operator. Basically, you assign to the final element, you assign null. So let's talk a bit about the array indexing. So you should know that the indices or the index of an array starts from 0 in Java, which we commonly say 0 indexing. So if an object to be removed is found at the nth position of the array, what is this value And how does it correspond to the argument that specifies the index of the array? Let's talk about it very briefly. So if objects 0, right? If this is equal to the item to be removed, then n is the first object. Because the first object is actually indexed by this 0. If objects 1 is equal to the item to be removed, then n is 2. Right? If objects I is equal to the item to be removed, n is actually equal to 1 plus I. So the subsequent code in the code snippet we discussed uses this Arraycopy method. So in the instance where the object or the element to be removed is equal to the ith element of objects, the arguments of Arraycopy methods are as follows. The source is objects. src pos is I plus 1. Because we are going to shift 1, cut everything on top of the current element, where the current element is deleted and the array shrinks by 1. Therefore, we have to copy everything from I plus 1 onto the same array, but the destination position is I, because we are removing the current value of I with the I plus 1th element. The size become, the length of whatever you copy becomes size of the array minus I plus 1, because we want to take all the remaining parts or all the remaining elements after the ith element on top of the ith element. So let's consider an example case where you have this orange at the ith position. And then if you call bag of fruits dot remove orange, this orange should be removed, resulting in this array where this orange is not there. So like you can see, this apple has moved by 1 position towards the left. Okay, next, let's now develop a test driver class to check whether the bag abstract data type and its array bag implementation are working as expected. Right. For this test program, we will first create a reference bag of objects and then add some fruits. And then we can observe and manipulate the contents of the bag. I'll briefly go through the code, and I invite you to pause the video and go through it in your own time as well to understand it in a bit more detail and try to implement it yourself. So as before, in this case, we have the class definition. This is called test bag ADT, and we have the main method defined here. So we instantiate bag of fruits, new array bag. Then we are adding some fruits. So we call bag of fruits dot add lemon, bag of fruits dot add apple. So like that, we have a large number of fruits added to this bag of fruits. So let's now try to get the number of fruits in the bag of fruits. So we try to print this string. There are some number of fruits in the bag. So you can get the number of fruits in the bag using this dot size method call. And you could print individual elements. So let's print the first element, system.out.println. The first element in the bag is use the get first method to get the first element in the bag. If you want to get the next one after the first one, which is the second one, the next element in the bag is, you call this method get next. Let's check whether there's an apple in the bag. There is an apple in the bag. It's true or false, right? So if you type this plus dot contains, bag of fruits dot contains, it returns true if there is actually an apple, and if there's no apple, it will return false. So it will type it is false if there's no apple. If you do the same with pears, right? Contains. You could remove something from the bag using the remove method. You could print the contents of the bag, right? Using print bag method. You could remove all the apples from the bag, remove all. So previously, when we implemented the remove method, it actually only removes just one. And here we have a new method called remove all. Let's look at, so there are some couple of methods, including remove all and print bag. There are some methods that have to be implemented as part of this class. First, to look at print bag, right? The method we use to print the contents of the bag. So input is bag, then you get the first object using get first, right? We have this initialization of the first element. It's not called initialization, it's just you getting the, we assign the first element into the object variable x. Then we have int I equals 1, it's just the index. So the contents are, we have a while loop. So as long as x is not equal to null, we do this while loop. We type element I is whatever x is. And then we assign x with a new value with get next, right? So it keeps getting the next element and printing it out with while incrementing the value of I. So then we look at the remove all method. So here, once we give a certain element, let's say an apple, you have to remove all the apples in the bag. So this is different from what we did previously. I'll go back to the previous remove method where we only remove the first instance of a certain fruit or a certain element. So going back in the first case, when we implemented bag in the class array bag, we have this remove method. It only removes the first instance of a certain object. So we have this for loop that goes from I equals 0 to until the end of the array. But as soon as we find the first object, when objects I equals this object, it removes it, resizes the array as appropriate, and returns true. Right? So it only applies for the first occurrences, for the first occurrence of this equality, right? When you first find the apple, remove the apple and return. You only remove one apple from the bag. That's not what we want with remove all. So it's a step ahead. So we simply use the remove method inside the remove all method. You could call it recursively. So basically what we do is we initialize this variable n equals 0, and then you remove the object from the bag and then increment n. This is inside a while loop. So this part is inside a while loop. So when an object is successfully removed, this returns true, right? So the while loop is intact, it's functioning still. So bag.remove apple removes the first apple and it returns true. And then it increments n. So in 0 before, and then it becomes 1. If there's another apple, since we are still in the while loop, it will remove the second apple, right? And then again returns true. Let's say there were only 2 apples. So it increments n, becomes 2. And then we are still in the while loop because it returned true before, but there's no more apple. No apples anymore. Then when you call back the remove apple, it returns false because you cannot remove an apple because there are no more apples. In that case, you exit from the while loop and you return n, which is, for example, was 2 in the example I mentioned. So have a thorough look at the source code that's shown in the slides and try to implement it yourself, right? And you can maybe do some changes and play around a little bit and observe the outputs. Here you have a sample output for the code mentioned in the previous slides. Same with this slide. Some of the outputs. Some more outputs. Now we come to the end, towards the end, last few slides. So in the test program that we've just looked at and hopefully you implemented, we defined 2 client methods. In our test driver program, we had this method called print bag that prints the contents of a bag. Then we have another method called remove all that removes all the instances of a certain object. So if you say remove all apple, it removes all the apples from the fruit bag. So the bag interface nor the array bag class, which implements bag interface, neither of them had the print bag method and the remove all method, right? However, we were able to define it in our test driver program. However, you should also note that both these methods, print bag and remove all, use the bag interface as a Java type. Here is a little exercise based on the lecture. So pause the video and attempt it yourself so that you have an improved understanding. If you are not sure about some answers, feel free to refer to the slides or even watch the video a second time. So in conclusion, in this lesson, you learned what a data type is, what abstraction is, and what an abstract data type is. And you also learned how we can build concrete data types from abstract data types. In the next lesson, you will learn about basic abstract data types called arrays and linked lists. So you already have some understanding of arrays, at least from the examples we looked at in today's lecture, but you will know much more. You will cover much more details about arrays and also linked lists in the next lecture.